You might be wondering, what's next in generative AI? Well, today's large language models, what they do is they predict a token given a sequence of other tokens. However, we're quickly moving up the thought abstraction tree where these language concept models are now emerging. And what that is it's able to reason within the sentence space. So if I were to talk about a topic, then in turn, every single time the LCM were to predict what I was going to say, it might be a bit different. But now what we're doing is we're predicting the probability of a concept giving a series of sentences that comes. But in general, both algorithms seek to predict the next sequence or token given a series of embeddings. Now this gives rise to the notion that LLMs and now LCMs are about data representation. Word embeddings are a way to represent words or sentences within these large vector spaces. So for example, say if I'm drawing a three-dimensional grid here, and I take the sentence, it's called artificial intelligence is a combination of art and science. Now perhaps it would land somewhere here. So now I have my X, my Y, and my Z coordinates. And this very effectively represents that sentence. And what I can do now is I can figure out what the relationship is between that sentence and maybe another one that could land about here. And I can take what's called a cosine similarity measure between this vector and that vector to tell me in concept, where are they? And there are many other ways of which I can take that measurement. But now let's take a step back. Arguably, one of the first types of embeddings that we have is called a frequency-based embedding. And what this does is this looks at the most prominent terms within a sentence, and it can represent how many times did that word actually show up. Right? And that was one of the first ways to help us identify the terms that are the most significant within a certain document. However, this really lacked the depth of a prediction-based embeddings that we now have today. And so the prediction-based embeddings are very much different. And what they do is we use models to actually project words into a higher dimensional space like we see here. And this refers to our function embeddings. But this is the type of embedding that's really dominant today. One of the most significant breakthroughs that happened was in 2013 with the introduction of the word-to-vector model. And then shortly thereafter, we saw the introduction of GloVe, Elmo, BERT, Albert, and there's even a new one called Sonar. But these techniques enabled us to not only represent the words, but also to capture what's called the semantic and the contextual value of where they land in this space or what their meaning is. Now you might be wondering, what do embeddings have to do with LLMs? Well, word embeddings convert text or sentences into these tokens such that an LLM can really understand the vocabulary. And what happens is these embeddings are here, so your sentences and words are inputs into that. Now, as it feeds forward into a stack, so I might have, let's say, 5 of these different types of encoders, and the data goes up, then it keeps going up into even more of these encoders as it happens. But you'll notice right in the middle, right, we have this multi-head intention, which tells us which tokens are most interesting rather than others. Then we go to a fully connected neural network. And when this happens, this helps to find all the different relationships between all of the tokens that were input and already that were biased towards what should we pay attention to. Finally, we normalize that text and then it's output. So now we have this encoded representation of the data that's already been tokenized in embeddings. And the next part of this is we then go over into what's called a decoder. And this is what this stack is. And you might be wondering, how are these two linked together? Well, the output of this, it actually goes into one of these attention heads. And whenever we do that, this influences what the decoder should pay attention to. But first of all, let's just talk a bit about how this works, right? So we also said that we have output, right, from the encoder. Well, that output can also become input from a previous stack of these encoders into the decoder here. And as this goes up, it follows much of the same process that happens over here, where we then go up and we might tokenize it a bit more, we might do some more embeddings to get into another space, and then we go into a multi-head attention, which tells us again, based on how we've trained the attention heads, what should we pay attention to? And then we go to a secondary attention, which, as I mentioned, this is influenced by the encoder. So the encoder has another representation that says, based on the decoder, how should we pay more attention to or less attention to which words in a sentence. Then we go up again, right? And then we do this neural network transformation to cross over and find the different relationships between the hidden neurons and the stack. And then we have an output. And the output will eventually be decoded back into some other text so that we then in turn as humans can better understand the output representation, so that either maybe even another agent can link up to it and then use that. But again, these stacks are stacked together. We have 5 of these that I just drew up, but then you might have 10 of those that are stacked together. And if there's a 2-to-1 kind of relationship, then you might interlace these inputs right over into this 2x stack of encoding. So that's a lot of where the art comes in, is how do we put these two encoders and decoders together. But in essence, this really gives us rise to the modern day LLM that most of us use on a daily basis. So now, what if these LLMs could reason at the concept level instead of at the token level? Well, this is where LCMs enter the field. So an LCM, it's trained to predict the next concept or even sentence. But now a concept, it represents a high-level idea, it's agnostic to language, and it's agnostic to modality. But this allows this hierarchical reasoning within the concept space. So here is the fundamental idea of how it works. So first, there are sentences at the very bottom. So I have sentence 1 all the way to sentence 5, and these represent different types of concepts. But here, this input, it goes up into an encoder, which in this case, we're going to use something called sonar, right? And then as we encode it into the sonar space, the sequence of concepts are then passed to the LCM to predict the next concept or sentence. And then the next piece of this is that the sonar embedding, it then is decoded into what the actual sentence structure is so that a human or even another agent can better understand it. And so there's even what's called a diffusion-based LCM. So just like image generation, the model, it slowly removes noise from the candidate concept until it's finally revealed at the very end. So what this means is that the last input sentence, which in this case would be S5, it's input into an LCM, and it's denoised over time. And the embedding is slowly revealed right at the very end. And this method, it also uses what's called a two-tower method, where it splits the denoiser and decoder, so we have 2 parts, much like what the encoder, decoder, or transformer architecture looks like. Now these LCMs, what it gets us, right, is it first allows us to reason in a much different way than before. So we can reason at the abstract level rather than the token level. It also allows us to go to this hierarchical kind of structure, right? That's very important so that these models can better understand what's happening, much like how humans do. And then we can also have much longer content that goes in. So we can call this even like a content, we can even call it a context window. But this is a higher level of reasoning that these sentences now have. Now, the other part that it also enables us to do is what's called a zero-shot generation, right? And this helps us to get specificity without the need for all these lower-level type tokens. And then also what I wanted to note too is that it's modality agnostic. So what I can do is I can pass in different types of sentences or different types of sound, images into this encoder, and Sonar can handle it with relative ease, and then the LCM can then in turn reason over it. So this story is really about what's called data representation, and it shows that our systems and methods are abstracting reasoning into this higher order thought levels. This will make AI much more generalizable, but also useful for everyday tasks.